Hello everyone, welcome to the session on Logistic Regression Coefficients. Before we jump into the Logistic Regression Coefficients interpretation, let us quickly see what Logistic Regression is, how it is represented graphically, and how the equations are. Yeah, so as we see here, this is the graphical representation of the logistic regression. You can see this is a sigmoid function, yes. You can say yeah, sigmoid, yes, function, logarithmic function. And you have x-axis as features and y-axis as the class label for the probability of that it is the predicted output, yeah. So it takes the maximum value of 1 and a minimum value of 0. So in equation terms, you can say y is equal to exponential of beta 0 plus beta 1 x. So beta 1 is the coefficient belonging to the x features. So beta 0 is the intercept. That is when the x is 0, how this would be represented, what would be the coinciding y point. So that will be depending on the beta 0 value, which will be, say, for example, it is 2 minus 2, then it would be below, or if it is plus 2, it will be above. Yeah, so you can say if we have x number of features, n number of features, so x1, beta 1, x2, beta 2, etc. So each of this coefficient belonging to the particular x feature. So now, if all of these features are 0, then the intercept would be beta 0. Yeah. So now y, as you know, class label, it takes the value either 0 or 1, and its probability is being measured from 0 to 1, and the total number of features is equal to the total number of coefficients. Yeah, this we will see directly in the Python code. Yeah. How do we interpret this logistic regression coefficients? It can also be represented as logarithmic of p, log it of p is equal to beta 0 plus beta 1 x1, beta 2 x2. Yeah. So this logarithmic of p is nothing but the log of p divided by p minus 1, which is the success by the failure. So we can call this as log of odds actually. So probability of, let's say, 6-sided dice game. So probability of getting 3 would be 1 by 6, and now the logarithmic of odds would be 1 by 6 divided by the failure, which would be 5 by 6. Therefore, it is 20%. So now you can say, like, let's interpret this in this way. Like you would like to go in a still mine or the sleeping mode, let's say. So it is defined by this equation, sleeping equation. So the probability of P, log it of P is success is getting sleep, going still, and failure is not in sleepy mode, or not in a still mind. So it would be given by this form, like 0.53 of meditating hours plus 0.023 of atmospheric sound. So when the meditating hours increases by 1 unit, say 1 hour, then accordingly this log it of p, that is its log of odds, will increase by 0.53. Similarly, when the atmospheric sound is maintained, that's the decreasing level. So if it is also its intensity is, say for example, atmospheric sound is very pleasant. So here I mean the pleasant sound. So the pleasant sound, not the noisy sound. If it increases the pleasant sound, then the logarithmic of odds will also increase by 0.23. So Therefore, this equation can be interpreted in this way. So the coefficients play a role in how much of increase or decrease the output will be, predicted output will be, in this case, the sleepy mode. So now I mentioned the total number, the coefficients, the number of coefficients is proportional to the total number of features. Let's see in the code. So this is the code. We have the logistic regression model defined here. Below, you can see from naive Bayes, also from the linear model of sklearn module. Then you can see here the total number of features is this much, and length of the coefficients or the total available coefficients, and what type of output it is, and what are all the how its shape is, and what are all the smallest and largest coefficients, etc. Yeah, that's the thing. And let's see its output, how it looks like. As you can see here below above, the total number of features is say 1503, and the length of the coefficients, the total available coefficients, is also same, so it's similar. So x features, x coefficients. So now the shape would be, of course, it's this one. It's an NumPy n-dimensional array. The shape would be this much, and smallest coefficients here, and the largest coefficients here. So this is actually written in the now let's take in this order. You can consider. So this is basically nothing but the last 10 items are directly outputted, but this is put in such a way that the last item will be represented. This is the last coefficient, largest coefficient, last one, and it's coming here. And then the next one would be this one, this one. So it's in the reversing order. So nothing but the way in which it is arranged is different with this output. So its shape is, of course, as we saw. I mean, how does the parameter or the attribute of this model look like? Let's see directly in the sklearn module. So you can see here the sklearn module. You will have the coefficient defined here, which is ND array or n-dimensional ND array of shape. It will have n 1, n features. So you can see here from our output, it's corresponding to that. You can see from our output, it will have n number of features. So 1, n features, that is already seen here in the output. 1, n features, and the intercept is given by this coefficient, and so we'll have one. Therefore, that's why we have it outputted in the code. Outputted in the code like of 0, which will have the first one, and it's sorted. And then we are taking the smallest and largest, and actually the coefficient will be 1, and the type would be, of course, ND array, and the shape would be 1, n features that we already checked it here. And the intercept value is can also be printed using this for model.intercept attribute, which are all the attributes of the model, logistic regression model. 1, n features for coefficients, and intercept is also 1, so it's just a one single value denoted here. Yeah. So Therefore, we can say that the number of features is equal to the total number of coefficients that we would be getting from the model logistic regression model. Yeah. Yeah. Thanks for listening.